Welcome back to mass transfer operations 2. We were discussing on humidification and air conditioning. In the previous class, we discussed on important terminologies, namely temperature, humidity and enthalpy, adiabatic saturation temperature, and then we learned how to read the psychrometric chart, and then we discussed something on classification of cooling tower. Now, we will be discussing on design calculations of cooling tower. Preliminary, we need to calculate the tower cross section required to take the given load of this warm water, which will be fed from the top of this cooling tower, and height of the packing material required to achieve the desired cooling. Means what will be the final temperature of the cooled water. For this, we need to assume two basic assumptions, like the rate of evaporation of water is much less than the rate of the water input to the tower. We assume that around 1% loss of the feed water takes place, and for that also we will be discussing that makeup water is there, and the second one, that evaporative or adiabatic cooling of the water occurs in the tower. So, the schematic of the water cooling tower is presented here in this figure. So, the hot water enters from the top of this cooling tower, like from here at we can say liquid at TL2 temperature with the enthalpy HL2. It enters from the top, and this one cold air, or we can say this one room temperature air, enters from the bottom of this cooling tower, like with the flow rate of Gs and temperature is Tg1. This 1 and 2 actually these are the stations. 1 for all the calculations we will take 1 as this bottom line and 2 as the top of this cooling tower. Okay. And the whatever the cold water will be coming out from the cooling tower, that will we say at the flow rate of L, and the temperature will be TL1 with enthalpy HL1, and the moist air which will be exiting from the cooling tower will be like this with this Gs flow rate, that is we can say this on dry basis, and temperature will be Tg2, humidity will be Y2 prime and enthalpy of H2 prime. For the simplicity of the calculation, first we assume one envelope like this envelope 1, where we can say this one we will take this bottom part of the cooling tower. This is we say we will take this envelope 1, and after that we will take one incremental height of dz, we can say this one or thickness of dz. So, across a differential thickness dz of the bed, temperature of water is decreased by dTL, and the enthalpy of the air will be increased by dH prime, as this water will be we can say this one some amount of water will be evaporated, and the evaporated water vapor will be added with this whatever air actually is coming from the bottom of this cooling tower. So, we can say this one the L will be taken as this water flow rate, that is we assume that it is a constant flow rate. The flow rate will be kg per meter square second, and Gs is the air flow rate, that is kg dry air per meter square second. And we also assumed in the beginning that whatever the water will be lost due to this evaporative cooling, that is negligible, that is almost 1%, and we can neglect that part also. And say across this thickness dz, say the change in enthalpy of this water will be L into Cwl into dTL, and change in the enthalpy of the air will be Gs into dH prime. So, we can say this one in the in that dz zone, or we can say this one with this slice, the differential enthalpy balance over this dz will be like this LCWL dt is equal to Gs into dH prime. So, we can say this one, whatever the enthalpy will be lost from the water, that same amount of the enthalpy will be taken by air, or some amount of water will be vaporized or evaporated, and this same amount of water vapor will be carried through this air. Now, this enthalpy balance over this envelope one, if I say this whatever the enthalpy is, we can say this one through this water is carried, that is we can say this how much amount of enthalpy is lost, L CWL into TL minus TL1, that is that is coming TL is actually we can say this one at any time the temperature of this we can say this one liquid, and it enters at TL1, that is why you can say this one the amount of enthalpy that is lost, that L CWL into TL minus TL1, that will be nothing but the whatever the enthalpy will be gained, that is by this air is Gs into H prime minus H1 prime. So, this is we can see the operating line for the air water contact. So, we will be keeping this one as the operating line. Okay. Now, we will be taking this entire this envelope like this one, the total cooling tower will be now taking into the consideration. There say this air is entering from the bottom, and say this one moist air will be leaving from the top, then this one hot air water will be entering from the top, and we can say this one cold water will be leaving from the bottom of this cooling tower. Okay. So, there we can say this one the enthalpy that will be this one lost from this liquid water, that we can say this one L CWL into TL2 minus TL1, that is the temperature driving force across this cooling tower is equal to Gs into H2 prime minus H1 prime, that is nothing but we can say this one enthalpy gradient this one across this cooling tower that is taken by this air. So, due to this we can say this evaporative cooling of this a part of this liquid water, that is hot water entering from the top. Okay. So, the equilibrium curve for air water system on TL H prime plane is the plot of the enthalpy of the saturation air versus the liquid temperature at the equilibrium. Now, rate of the transfer of the water vapor to air in the differential volume, that is we have taken this dz as the differential thickness, and if we take this in that differential thickness, what is the differential volume? So, we can say this one Gs into dy prime is equal to Ky prime into A bar into yi prime minus y prime, whereas this yi is this we can say humidity at the interface. Okay. So, the decrease in temperature of the air for the sensible heat transfer to the water is nothing but minus Gc into Ch into dTg, that is equal to Hg into A bar into dz into Tg minus Ti. So, differentiating that equation which we this one obtained for the total enthalpy of the system, that is we can say this H prime is equal to Ch into Tg minus T0 plus y prime into lambda 0, where T0 is the we can say this one 25 degree Celsius, that is nothing but 1.005 plus 1.88 into y prime into Tg minus T0 plus 2500 into y prime, that in the previous class we have already derived that enthalpy equation. Now, we will be differentiating the equation and we will be multiplying with gas flow rate, that is we can say this is dry air flow rate, that we will be getting Gs into dH prime is equal to Gs into Ch into dTg plus Gs into dy prime into lambda 0, that is we will be obtaining by differentiating this equation H prime is equal to Ch into Tg minus T0 plus y prime into lambda 0. So, we can say this one Gs into dH prime is equal to Gs into Ch into dTg plus Gs into dy prime into lambda 0. Just by manipulating these two terms of the right hand side of this equation, we will be getting Gs into dH prime is equal to minus Hg into A prime into dz into Tg minus Ti plus Ky prime into A bar into dz into yi prime minus y prime into lambda 0. That is nothing but k y prime into a bar into d z, in the bracket we will be getting h g by k y prime into t I minus t z plus y I prime minus y prime into lambda 0. And by manipulating this, we will be getting ultimately that k y prime into a prime into d z into c h into t I minus t 0 plus c h into t 0 minus t z plus y I prime into lambda 0 minus y prime into lambda 0. And from there we will be getting ultimately that g s into d h prime is k y prime into a bar into d z into h I prime minus h prime. And now we will be getting this height of this packing in the cooling tower, that we will be getting by just integrating this equation with respect to these enthalpy values, that is d h prime by h I prime minus h prime. This integrating this one from h 1 prime to h 2 prime, or we can say this one from bottom of this tower to the top of the tower. If we integrate this one, we will be getting k y prime into a bar by g s into the integration of this d z, that is nothing but we can say this one from 0 to z. Z, say we have taken this differential height as d z. So, that is why whenever we will be integrating across the entire tower, we will be getting this integration. If we integrate this one, 0 means this bottom line, that is we can say this one station 1, and 2 means this top of this cooling tower, and the total height will be z. So, we will be getting this total integration of this d h prime by h I prime minus h prime is equal to nothing but k y prime into a bar by g s into z. Okay, from there we will be getting this height z. Now, this number of gas enthalpy transfer units, the NTG, that will be nothing but we can say this one whatever the transfer units, that is if we integrate this one from in terms of we can say this one from bottom to top of this cooling tower, then it will be a h 1 prime to h 2 prime, and that is d h prime by h I prime minus h prime. And height of this gas enthalpy transfer unit will be h t g, that is nothing but g s by q I prime into a bar. So, we can say this how the height of the cooling tower, we can say this one effective height of the cooling tower z will be this multiplication of this number of gas enthalpy transfer unit into the height of the gas enthalpy transfer unit. So, nothing, that is nothing but h t g into n t g. So, volumetric flux or enthalpy transfer, this one we can say this one volumetric mass, or we can say the enthalpy transfer coefficient should be known. So, that we can say this one we will be getting this, if we know this one k y prime into a prime, then only we will be able to get this h t g. Okay. So, then h t g can be estimated from the given mass transfer rate. So, there is no direct relation available between the enthalpy of the bulk gas H prime and that of the H I prime. So, we can say this one integral cannot be evaluated analytically. So, for this numerical or graphical evaluation of the integral, we have to know the value of the H I prime. That is, we can say this enthalpy value in all the interfaces or in all the places we need to get the enthalpy values, or we can say the interspatial enthalpy for a set of values of the H prime. So, let H L A bar is volumetric heat transfer coefficient on the water side, then that will be G S into d H prime will be equal to L into C W N into d T L, that is nothing but H L into A bar into T L minus T L I. Okay. So, from there we can say k y prime into A prime A bar into d z into H I prime minus H prime is equal to minus H L into A bar into d z into T L I minus T L. Just we made this equal to minus this one right hand side minus, that is why we have changed the direction of these temperatures, that is T L I minus T L, because we know that the temperature of the liquid will go on decreasing from the top to the bottom, and just by manipulation we will be getting H I prime minus H prime by T L I minus T L will be equal to minus H L by Q I prime. So, a point actually T L and H prime on the operating line meets the equilibrium line at the point T L I and H I prime. We will be showing this one graphically nicely whenever we will be doing the step by step calculation. just for the, we can say this one step by step procedure we are showing there, and where this point T L and H prime will be there, and where we will be getting the, we can say this one will be meeting this equilibrium point, that will be this one explaining clearly. So, substituting this G s into d h prime is equal to L into C W L into d T L in equation G s into d h prime is equal to k y prime into A bar into d z into h I prime minus h prime, we will be getting L C W L into d T L is equal to k y prime into A bar into d h into h I prime minus h prime, and we will be getting this integral of this d T L by h I prime minus h prime from T L 1 to say T L 0 is equal to k y prime into A bar by L C W L and the integral d z from 0 to z. So, that is nothing but say k y prime into A bar by L C W L into z. This equation is called this Merkel equation. Now, a simplified designing equation based on the overall enthalpy transfer coefficient also is there, and sometimes we need to do that also. If we have the overall mass transfer coefficient like this capital K y prime, if it is used, then differential mass transfer equation will become this G s into d h prime is equal to capital K y prime into A bar into d z into h star prime minus h prime. Here h star prime actually is the enthalpy of the saturated air at T L, that is we can say this bulk liquid temperature. Then we will be getting that same Merkel equation like h 1 prime to h 2 prime, that if we integrate this d h by h star prime minus h prime from h 1 prime to h 2 prime, we will be getting capital K y prime into A bar by G s and the integration from d z from 0 to z. So, we will be getting capital K y prime into A prime A bar by G s into z. So, this is we can say this overall enthalpy transfer unit NTOG. Now, this expression of the overall enthalpy transfer coefficient in terms of this individual coefficients. Say we know this Q is equal to small k y prime into h I prime minus h prime. So, this is nothing but h L into T L minus T L I, that is equal to capital K y prime into a h star prime minus h prime. So, from there just by manipulation we will be getting h star prime minus h prime is equal to h star prime minus h I prime plus h I prime minus h prime. Just to make this one in the form of this, we can say this q by k capital K y and small q by small k y prime. Just we will be getting q by capital K y prime is equal to q by q into h star prime minus h I prime by h L into T L minus T L I plus q by small k y prime. So, we are able to correlate this one overall mass transfer coefficient and this we can say this one enthalpy transfer coefficient with the individual enthalpy transfer coefficient in this form, or say 1 by capital K y prime is equal to just by eliminating q from both the sides, we will be getting 1 by capital K y prime is equal to h star prime minus h I prime by T L minus T L I plus 1 by small k y prime. So, we can express this Merkel equation as this capital K y into A bar into V by L is equal to, we can say this one d T L by h I prime minus h prime integrating from T L say 1 to T L 0. The left hand side of this equation we can say this one capital K y prime into A bar into V by L is called tower characteristics, where V is the active cooling volume per plan area. So, this tower characteristic, or we can say this one capital K y prime into A bar into V by A L by say capital K y prime into A bar into V by L, that is we can say tower characteristics has so many features like an increase or decrease in the wet bulb temperature of the entering water, due to this atmospheric condition like this say if today this climatic temperature is very low due to some weathering effect, or say maybe today the temperature of the atmosphere is very high, then we can say this one whatever the wet bulb temperature that may be more or less, but that cannot change the tower characteristics, because that capital Ky into A bar into V by L is independent of the wet bulb temperature of the entering water. So, that cannot be changed due to this weathering condition or climatic condition. Then an increase in cooling range cannot change the tower characteristics. It can increase the approach. We will be discussing more on the cooling range and the approach near future. And a change in the L by G, or we can say this a liquid flow rate to the gas flow rate, can change the tower characteristics, capital Ky prime into A bar into V by L. So, that only we can say this one. If we want to change the tower characteristics, we need to manipulate the liquid flow rate and as well as the gas flow rate. Now, we can say fill height, or we can say this inside this tower, whatever the filling material will be adding, that depends on the tower characteristics L by G, and these are correlated by the following equation. This tower characteristics is C into Fh into L by G to the power n, where we can see this one capital C and small n are the constants, and these are solely dependent on the tower fill material. Whatever the material actually will be used to fill the tower, that will give this value of C and n. Now, we will be discussing the step by step design procedure of the cooling tower. That this is very important, we can say this one part of this cooling tower design. So, we need to do the step by step procedures to get the height of this cooling tower, as well as this we can say this one area of this cooling tower. So, firstly we need to specify the inlet and outlet temperature and the flow rate of warm water, that we have to specify, or we can say this one in the beginning we need to get the values of the, we can say this one what is the flow rate and what is the temperature, inlet temperature, and what is the outlet temperature, means what we require, or we can say this one if the cooling tower is operating in this climatic condition, then what will be the outlet temperature of this warm water, means this one whatever the cold water will be coming out, that temperature we need to specify. Then we have to select the design value of this dry bulb and wet bulb temperature of the air. So, it is entirely dependent on the, we can say, geographical location. So, it will be changing from one location to another location. Okay. Then we need to draw a equilibrium curve, that is we can see the saturation humidity curve, that is H prime versus T, that will be showing in this next slide. Will be showing this one how to draw this equilibrium curve. The enthalpy data are calculated using the Weber equation for water and the physical properties of the air and water vapor, using this formula H prime is equal to 1.005 plus 1.88 into y prime into Tg minus T0 plus 2500 into y prime, that will be in terms of kg per kilojoule per kg, and T0 will be taken as the 25 degree Celsius. And also you see equilibrium line also for air water system, that is we can get from the psychrometric chart also we will be able to get. Okay. Now, this we need to locate the lower terminal of the operating line B on the TL this one plane by point TL1 and H1 prime. So, this one we can say this is the, we can say this one lower point of this, we can say operating line, this one. This we know that's TL1 and we know this how much amount of enthalpy is there H1 prime. So, we need to locate this point B. Okay. And say this point indicates the condition at the bottom of the tower, means from where this liquid actually cold water will be exiting from the cooling tower. So, we need to get this point. If we know the enthalpy value, if we know the temperature, at which temperature it will be exiting, then we will be able to get this what is called that point B. Now, you see this we need to draw a tangent actually to the equilibrium line through point B. Like this, from point B we need to draw this tangent, say this one, say equilibrium line we have this one, and we will be drawing this tangent. Okay. So, from point B actually we will be drawing this tangent we need to draw. See this the slope of the tangent gives the ratio of the liquid and minimum gas flow rate. So, hence minimum gas air rate is actually calculated, but actual air rate is taken usually 1.25 to 1.5 times of the minimum. So, if it is already supplied by this manufacturer, then we can say, or we can say this one from the vendor, then I think it is not required. And then upper terminal of the operating line is located by the point A, that is we can say this one from where this liquid water, hot water actually is fed from the top of this cooling tower. So, that is we can say this one, whatever the slope actually we have determined this in the here. So, that A point is this one. So, we can say this one, that is indicating that whatever the TL2, or we can say this one hot water temperature and whatever the enthalpy value H2 prime. So, this is we can say this one, the top of this cooling tower condition, it is designated in point A. Okay. So, now you see this one and so it can also be located by calculating the top end enthalpy H2 prime from equation like LCW into TL2 minus TL1, that is we obtained this one from the envelope 2, that is nothing but equal to Gs into H2 prime minus H1 prime, as this LCW into TL2 minus TL1 is equal to this one Gs into H2 prime minus H1 prime. Okay. Now, you see this one, we need to evaluate the integral because ultimately we have to calculate this NTG, that is we can say this one will be getting this integral dH by H1 prime minus H prime from H1 prime to H2 prime, because that is the number of gas phase enthalpy transfer units, and we need to calculate the height of this we can say the gas phase enthalpy transfer units, that HTG, as we can say this HTG equal to Gs by small k y prime into A bar, and this small k y prime A bar and HL into A bar, these are required, that will be actually supplied for the calculation of the cooling tower for air water system. So, a set of these parallel lines we can say the of the slope minus HL into A prime by k y prime into A is drawn between the operating line and the equilibrium line, just like we will be drawing this shape, all the parallel lines like this. So, we will be drawing a set of this all parallel lines, we will be drawing this one, all these we can say this one, all the parallel lines will be drawing here. Okay. So, a set of the parallel lines of the slope minus HL into A bar by k y prime into A bar is drawn between this operating line and the equilibrium line, and H prime and H I prime are taken from the terminals, and integral is calculated numerically, or we can see this one from graphically, where we can see this one will be getting NTG is equal to TL1 to TL0, that is integrated for DTL by Hi prime minus H prime, and HTG is equal to L into CWL by small k y prime into A bar. If the overall enthalpy transfer coefficient capital K y is known and used, then tie lines will be vertical like this, whatever the tie lines were all these were parallel, this one what is called from the operating line, here will be all this will be in the vertically, these will be placed, and for a given value of this H prime, value of this H star prime also is given by the point on the equilibrium line vertically above it. And then the integral of the equation, this dH prime by H star prime minus H prime from this H1 prime to H2 prime, that will be nothing but NTOG, that gives the number of overall transfer this one what is called units, and the height of the transfer unit HTOG will be by Gs by capital K y prime into A bar, or we can say this one HTOG will be in terms of liquid flow rate, that is L into CWL by capital K y prime by into A bar. So, from this we will be getting. So, the packed height is the product of this height of the transfer unit and the number of transfer units. So, we will be doing this one, and we need to know these two important terms like this approach and range. So, this approach is nothing but we can say this, it is the difference between this cooling water temperature leaving cooling tower and this wet bulb temperature of the inlet air, which approaches to wet bulb temperature in degree Fahrenheit. That is nothing but we can say this TL1 minus TAS. So, for getting small approach, cooling tower height must be increased. So, to achieve this zero approach, theoretically infinite number of packing height is required. If we talk about this range, or simply we can say this cooling range or purely range, that is the difference in the inlet hot water and outlet cold water temperature, that is nothing but TL2 minus TL1. Now, this approach to wet bulb temperature, or we can say this one approach, that is in terms of degree Fahrenheit, that is if it is 15 to 20 degree Fahrenheit, then we can say this cooling range will be around 25 to 35 degree Fahrenheit, and the typical packed height requirement will be 15 to 20 feet. If we say this approach to wet bulb temperature will be in the range of 10 to 15 degree Fahrenheit, then cooling range will be around 25 to 35 degree Fahrenheit, and packed height will be around 25 to 30 feet. And if we say approach to wet bulb temperature will be 5 to 10 degree Fahrenheit, then cooling range will be 25 to say 35 degree Fahrenheit, and this packed height will be in the range of 35 to 40 feet. Now, you see this one, we need to understand these two other terms like this evaporation loss and this blow down in the cooling tower. That is blow down means we can say this one, whenever one cooling tower is installed, mostly it is placed on the open air, and say we know that the role of the cooling tower is to cool down the hot water that is coming out from the different chemical processes, or we can say this one maybe from turbine of this power plant unit, and whenever it will be coming to this cooling tower, this we can say this one 2%, around 2% water actually evaporated, maybe around 1 to 2% water evaporates, and in the we can say this one louvers, or we can say this one different sides of the cooling tower, and also at the bottom huge amount of we can say this one algal growth take place, as well as the some amount of the suspended solids also are deposited there. So, in the long run it increases the solid content in the circulating water. So, some dust particles also come from the environment and mix with the circulating water, but the solid content of the this one cooled water must be kept under a certain limit to avoid the scaling or fouling on the heat exchanger or equipment, or anywhere this cold water will be used. So, a portion of this we can say this one water, a part of the circulating water is drained from the bottom of the cooling tower periodically to discard the deposited solids from the cooling tower, and the losses due to this blow down, evaporation, drift and leakage are compensated by this adding this makeup water. So, this makeup water is added like this, maybe 1 or 2% of the total water flow rate. So, we can say we can do easily this water balance in the cooling tower like this. Total M is the makeup water is nothing but is the summation of this B means this blow down rate, D is the drift leakage, and A is the evaporation. So, drift leakage also is one of the we can say this one losses whenever it is flashed from the top of this cooling tower, some amount of we can see this one water will be flashed, and that will be we can say this one lost from the cooling tower. It is not coming down to the cooling tower through the mainstream, but some amount will be this one lost to the environment. And the solid balance we need to do the solid balance like M into C1 is equal to B plus D into C2 plus E into 0, because see this whatever evaporated, that is it is not containing any solid. So, we can say this one B is nothing but this blow down is equal to E minus D into R minus 1 by R minus 1, where we can say this one a small r is equal to C2 by C1, where C1 is the dissolved solid concentration in the makeup water and C2 is the dissolved solid concentration in the circulating water. And this there is one thumb rule for the calculation of the evaporation loss, that is E is equal to we can see this water flow rate into the range whatever the this cooling range is there in degree Fahrenheit into 0.00085 gallon per minute, that is the thumb rule, and in most of the cooling towers this holds good. The other design characteristics are like pump horsepower, then fan horsepower, then source of the makeup water and the drift eliminators. These also we need to consider during this we can see this one design of the cooling tower. And the nomenclature that is used for the entire cooling tower design like A bar is equal to contact area per tower volume, that is meter square per meter cube, and CWL is equal to heat capacity of the liquid water in kilojoule per kg Kelvin. Then GS is equal to air rate, that is we can see this kg dry air per meter square second, that is used in the dry basis, and Hg, small hg is equal to heat transfer coefficient of the air film, that is in kilojoule per meter square second Kelvin, and small HL is equal to heat transfer coefficient of the liquid water, that is kilojoule per meter square into second Kelvin, and small kg is equal to mass transfer coefficient of the moisture transport, that is kg per meter square second, and CWL is equal to overall mass transfer coefficient, that is in kg per meter cube second, and capital L is equal to water flow rate, that is in kg per meter square second, and active cooling area, active cooling volume per plane area, that is meter cube per meter square, that is the capital V, and Y prime is the humidity, that is kg moisture per kg dry air, and say YW prime is equal to saturated humidity, that is kg moisture per kg dry air, and Z is the cooling tower height, and that is in meter, and lambda W is equal to latent heat of evaporation of the water, that is in kilojoule per kg, and this nu H is equal to humid volume, that is meter cube per kg dry air. So, thank you. In the next class, we will be solving one problem on the cooling tower.